Greetings! In today's lesson, we will discover how to determine the intersection point of function graphs. This guideline will be valid for all function graphs. Yet, we together know the graph of a linear function. We know that the graph of a linear function is a line. And we will determine the intersection point of the graphs of two linear functions. Once again, I draw your attention to the fact that we will use this rule when working with graphs of other functions. But let's return to the graph of the linear function, and remember that the linear function is shown by the following formula: x plus b plus c is 0. And we mentioned that this is the standard form of a linear equation with two variables. But we mentioned that we can also write it in another form. If I retain the variable y on the left and shift all other terms to the right side, then we get my linear function appears in the following form: y equals mx plus b. And we talked about the fact that this function expresses the linear function graph. Why did we write our linear function this way? The reason is that in mathematics there are principles that allow us to find the intersection point of two lines. First of all, we can say that to find the intersection point, we can plot the graphs of these functions. And we will do this and then find their intersection point. But in order to determine the intersection point and ensure that these function graphs intersect, we must understand the following condition. This is the criterion for the intersection of two linear function graphs. So I will write it down. If the first function is written as y1 equals m1 times x plus b1, and the second function is written as y2 equals m2 multiplied by x plus b2, then the graphs of these functions will indeed intersect. I will mark this with the following notation. Only in the case that m1 is not the same as m2. Therefore, if the coefficients of these functions differ, then these graphs will surely intersect. These graphs may also be parallel, and they will only be parallel if m1 equals m2. And in the previous lesson, we found the solutions to systems of equations using the graph of the function. And we looked at the case where the function graphs did not intersect. In this situation, I observed that the coefficients for the variable x were equal. There is also a third case where the function graphs will coincide, but in this case the coefficients and the constant terms must be equal. Let's verify this rule together. If I consider the following functions, and I need to find where these graphs intersect. The first graph is y equals 3 minus x. And the second function graph is y equals negative 3 plus 2x. We need to plot these function graphs. We know that to create a graph of a linear function, we only need to take 2 points. Plot the coordinates of the 2 points and connect them. As a result, we will get the graph of the linear function. We set a value for x. I will note that x equals 0. Then in this case, if I substitute 0 for x, y will equal 3. Let's substitute a value equal to 3 for x. In this case, 3 minus 3 is 0. And I got 2 points. The first point is the point with coordinates 0, 3. 0, 3. Here's the point. The second point is 3, 0. Now let's connect these 2 points, and as a result, we will get the graph of the linear function. Connecting. We draw a line through these points. Once again, I draw your attention to the fact that if you don't need to mark these points on the coordinate plane. I draw your attention to the fact that if you find points with these coordinates on the coordinate plane, you must draw a line through them. In this way, you demonstrate that the line can continue in various directions. Now let's construct the graph of the second function, y equals minus 3 plus 2x. Here we also assign a value to x and determine the corresponding y value. If I substitute 0 for x, then the value of y will be minus 3 plus 2 times 0. That's minus 3. Let's substitute the value of 1 for x instead. Then it's minus 3 plus 2 times 1. Thus, we will arrive at minus 1. Now let's mark these points on the coordinate plane. The first point is 0 and minus 3. 0 and minus 3 is the first point. And the second point is 1 and minus 1. 1 and minus 1 is this point. If I connect these 2 points with a line, we see that our graphs intersect. Let's draw the line, and we notice that the graphs of our functions meet at one point. And we need to find the coordinates of this point. It's not difficult to find the coordinates of this point. Finding the coordinates of this point is not complicated. For x, this value is equal to 2, and for y, this value is equal to 1. So we have a point which we will call A. This point will represent the intersection of our function graphs. We will note that the graph of the first function, y1, and the second function, y2, intersect. At some point A, and the coordinates of this point A are 2 and 1. But prior to plotting the graphs of these functions and determining this intersection point, we must first analyze how our linear functions are expressed. I want to highlight this point. In order to find this intersection point, we initially had to compare the coefficients associated with the variable x. In the first function, x has a coefficient of 1, and in the second, it is 2. As per our condition, if the coefficients are not equal, the graphs of these functions will intersect at a single point. Then we can draw the graphs and find the intersection. Thus, to find the intersection point of linear function graphs, first pay attention to the coefficient of the variable x. If these coefficients differ, we can then draw the function graphs and locate the intersection point. But we can find the intersection point without plotting these functions, using a method called the algebraic method. What does it involve? Let's note it down again, the functions. The first function is y equals 3 minus x, and the second function is y equals minus 3 plus 2x. Pay attention to the fact that the left side of both equations equals y. Then there is a wonderful rule in mathematics. If the left sides of the equations are equal, then the right sides must also be equal. Therefore, I can set the right sides equal to each other. 3 minus x equals minus 3 plus 2x. And solve this equation for one variable. Let's solve this equation. We will move 2x to the left side. Negative x minus 2x equals minus 3 minus 3. Then, as a result, on the left side we will have minus 3x equals, and on the right side, minus 6. And you see that to find x, you need to divide minus 6 by minus 3, and x will equal 2. As you can see, we did not draw the graphs of these functions. However, we first analyzed the coefficients of x and saw that if these coefficients are not equal, the graphs of these functions intersect. Then we do not build function graphs, but equate the right sides. Thus we find x. Let's compare our answers. When we plotted the graphs of linear functions, x equals 2. So in this instance, x is 2. How can we calculate y? For any of these equations, we plug in the value of x equal to 2. Let's write the first equation together. Y is equal to 3 minus x. And we substitute the value of x, which is 2. 3 minus 2 equals 1. As a result, y equals 1. Let's return to our answer. Y is 1. As you can observe, with the second approach, we found the correct answer more swiftly. In our next lesson, we will work on another exercise and locate the intersection of the function graphs. That concludes our lesson for today. Goodbye and see you soon.